Welcome back. In the previous lesson, we learned about the different types of joints. And to do that, we looked at that robot that looks like an R2D2 from the official ROS2 tutorials. You should check it out. It's a very good tutorial. And the reason I used that one instead of SHL1, my robot, is that that tutorial showed the four main different types of joints. Okay, if you remember them, there were what we had fixed joints. We also had revolute, we had prismatic, and we had continuous. So I wanted to show you those four joints, sorry, with that tutorial because my robot doesn't have prismatic joints. So now that we're ready to actually create a digital twin of my robot, we're gonna use my robot instead of that other one. But to introduce the joints, I wanted to use that other tutorial. Anyways, so here we have a visual representation of SHL1, the robot, and that's what we're gonna try to clone or replicate today. All right, so this lesson is called From Measurements to Macros, and soon you will learn why. And so the requirements for this lesson are that you install ROS2. So here is an excellent installation guide. I'm not going to go through it. It's very well documented. Again, this is not a ROS2 course. And then the next thing you need to do with your own robot, for SHL1, I will provide the measurements to you. But if you're working with your own robot, you are creating a digital twin of your own robot, you have to start by measuring the robot, right? Because you want the twin to be as accurate, as similar as the real one. So it needs to have the same dimensions. So here is SHL1, the real one. Two pictures of it. This is not simulation. And then I went on a while ago with the measuring tape, and I took measurements of everything, like measurements of the chassis, the wheels, the cabinet, those bars that create this stand for the LiDAR, etc. Now, SHL1 is fairly complex. It has a lot of stuff. Today in this lesson, we're only going to concentrate on modeling the chassis, the wheels, and the main cabinet. Okay, we're gonna for now ignore the sensors. This will be later. We're gonna add them later, but we're gonna concentrate on the chassis, the wheels, and the main cabinet. So here are the measurements. The main chassis has a length, width, and height provided here. Then there's a battery, which we also are going to model, and it's the offset is like that. So it means that it's moved from the center of the chassis by this much, very little, and it's also going down, right? There's a Z offset, meaning that it's below the chassis. So it goes down by this much. All right, so then the cabinet has the following dimensions and also has an offset. The cabinet is above the chassis, so the Z offset is positive, right? And the wheels have this radius, this width. The wheelbase is the distance between the front and the rear wheels. Okay, and we're gonna use this to also calculate the distance from the front and the middle wheels, right? But this is from the front and the rear or the back wheels. And the track is the distance between the left and the right wheel. So we need this in order to create our robot, twin with URDF. Okay, so you can read this tutorial, but I just wanted to show you the table, but you can go through this tutorial by yourself. But in the video tutorial, I want to kind of help you out getting started with the code. So all of the code for the course will be in this repository. So we're gonna clone it, and I'm just gonna show you a little bit of ROS and ROS2 here, but just a little bit. This is not a ROS course. So I'm gonna clone this in documents. So I'm gonna type git clone. If you're not familiar with these commands, I suggest you start learning all of these things, because if you want to be a real robotics engineer, you need to know git and many other things. So I'm going to clone it. Okay, and then I'm gonna go to RSC course, but inside of it there's a ROS2 workspace. And again, if you don't know ROS yet, go through the ROS tutorials. They talk about all of these things there very clearly. So this is not a ROS course. I'm not gonna teach you all the details, but there is a ROS2 workspace, so go to it, and then you need to build the workspace. And again, these are things that you can learn by just following the basic tutorials, free tutorials of ROS2. So Qualcomm build Simulink install. This will build the workspace, and then we need to source the workspace. So again, this just ROS things that you can learn by yourself. And then I'm gonna show you the end product. So ROS2 launch, RC display. So this is the final version of SHL1. We're not building this one. Remember, we're gonna just concentrate on the lower part, the chassis, and the cabinet. Okay, but I just wanted to show you the final product, and you can actually have access to it from the repo already. Okay, now we're gonna start with the static part. Okay, so here there's a tutorial part 1 URDF. Okay, so this is a URDF, and a URDFs always start with a robot tag, and they're materials, right? Because most of the parts of the robot are black, so there's a material. Don't worry about that. You can learn about this by yourself. Most important is that we're gonna create a base link. Remember, links are like the bones, the physical parts of the robot. And most robots in ROS2 have a base link. And usually base link is like the main chassis, the main body. That's usually where the center of mass is. So it's like the most important physical part of the robot. And there's a convention. Normally you call it base link. So this is the main chassis. And if you remember the dimensions from the table, basically they're here, right? So here are the dimensions from the table. So the length, the x-axis, the width, the y-axis, and the height, the z-axis, all of them are there. Okay, so that's the box. Why a box? A box is like a rectangular prim, right? It's like a rectangular 3D shape, and our chassis is just that. And usually the base link is at the origin, so the rotations and the translations are all set to 0, and it's black. Okay, now I don't talk too much about collisions yet, but just know that the visual aspect without collision will make your robot just be like a ghost, right? There's no physics. You can go through it. So we're gonna talk more about collisions later, but collisions is what makes your robot not fall through the floor, or it gives it like the physical properties. Don't worry too much about that. Then there's also a base footprint. Is a special link that has no particular shape. You see, it's empty. It's just a link. We're gonna talk more about that in later lessons when we talk about navigation. So don't worry about it too much right now. But there's a joint, a fixed joint between the base link and the base footprint. Not to worry too much about it. It's mostly for navigation and other stuff. So the most important thing is we have a base link, which is the chassis. And then I define the what I call the armario, which is the cabinet. Okay, it's the cabinet. And again, here are the dimensions of the cabinet, the width, height, length, everything. It's also black. And by the way, the collision sizes or geometry are the same as the visual one. Unless you for some safety reasons you want to make the collision slightly bigger than the visual, but normally you don't make it smaller. And usually it's just the same. We're going to talk more about collisions later, so don't worry. Here is the most important thing. This is the first actual joint. Right, the other joint with base footprint, base link, that was more like a logical joint for navigation purposes. But this is an actual real joint that connects two real physical elements: the base link, which is my chassis, with the cabinet. Okay, and here are the offsets. Remember, we were talking about some offsets from the cabinet in relation to the the chassis. So here it is, that offset, right? There's no rotation, just that offset. So that is the first link, first physical link between two components. And then there's a battery. And the reason why I included the battery is because the battery actually has like a trapezoidal shape, like a trapezoid. And there's no such shape in URDF. You cannot define a trapezoid. You can only define like a box or like a cylinder or like a sphere. There is no trapezoid. So in that case, I had to use some CAD tool to design a trapezoid and export that as an STL. So it's like a mesh. So I wanted to show you that to let you know that all robots are not composed of those basic shapes that URDF offer. If you want something more complex, and when we use our sensors, like that will look like the actual sensor, like the cameras and stuff, you actually use meshes, which can be designed with CAD software. This is just a very simple trapezoidal shape, but still had to be created outside because URDF doesn't support that shape by default. So here, instead of a box or something like that, we have a mesh. It's black, and the collision is the same mesh. Okay, and then we have a joint, fixed joint that connects the battery to the base link. Right, the battery is the child, just like the cabinet was the child, and the parent is the base link. And this defines a tree structure that we're gonna look at in a moment. All right, so this is the fixed part of the robot. So let's have a look at it. So if I now run TP1, so this is what it looks like. Okay, so we have the chassis, which is the rectangular part. Then you see the trapezoidal part here. This is the battery, and then this big square here is the cabinet. Now the real SEDRAD has some columns here, like some cylinders that like represents the support, right? But you don't really have to have that, right? Technically, this is a fixed link between the two. When the chassis moves, this guy will move with it. But if you want to make it more realistic, then you add all the support parts, but you don't really have to. I did because I wanted it to look like as close as possible as the real thing, but you don't have to. And then you can see the tree structure here. So you see this is the reference frame, or the coordinate frame, or the triad for our Mario, for the cabinet. This one here is for the base link. This one here is for the battery, and this one here is that footprint thing that you don't have to worry too much about right now. You can actually enable the names, and you can see them there. Okay, and the robot model has a similar structure. If you enable it, it also has the links here, right? I can deactivate our Mario. I can deactivate the battery. I can hide the base link. Okay, and it's a tree structure. You can see it here. The base footprint is the parent. Don't worry about that. For now, all we care about is that we have a base link, which is the parent of our Mario and the battery. Okay, cool. So this is for the fixed part of the robot. I'm gonna stop this video here. I don't want to make it too long, so I'm gonna create another video for the rest.